Hey, what's going on, Science 10s? Mr. Walton here. Today we're going to look again at the motion of a couple cars. Just keep in mind, here's the situation. We got the blue and the red car. They both want to go to the same place, but unfortunately, the shortest route there, if we're going, north on 91st Street, it's got construction on it. So the blue car is going to take a chance. It's going to go through the construction. The red car is not going to take a chance. It's going to go all the way around the construction. And so we're going to see what happens. You've already seen this before, but we're going to see what happens and see who gets there the fastest. Okay, so we've seen that video before. That's interesting. I got a couple questions for you. Which of those cars had the greatest speed while they were going on their journey? What is speed? How do you define speed? Do you know how to define speed? I don't know. Probably we're going to be able to want to define it properly and actually be able to go through and see how to figure it out quantitatively. So that means with some numbers. Here we go. Okay, so first part of our notes, we're actually going to talk about something other than speed here for a second. We want to talk just really quickly about something called uniform motion. Now, uniform motion is a type of motion. It's a very specific type of motion. It's when an object is traveling at a consistent speed, so the same speed the whole time, and in a straight line. And so we want to ask ourselves, okay, was one of those cars traveling with the same speed the entire time? Let's kind of go back and let's watch it again. Okay, so yeah, for sure, one of those cars was traveling with the same speed the entire time and in the same direction. So that blue car was traveling with uniform motion because it was here, let me choose blue. It was heading in one direction the entire time, and it started off going a very specific speed and it finished going a very specific speed. But that red car started going this way, then took a right-hand turn, then took another right-hand turn. And so the red car was not traveling with uniform motion. Let's think of some other examples of some objects that might be traveling with uniform motion. So a car driving down this, just a regular car driving down the street. Well, have you ever traveled in a car and stayed the exact same speed in the exact same direction for an extended period of time? Maybe, but probably not. Okay? So cars driving down the street, it's pretty darn hard to be able to go the exact same speed in one direction the entire time. Let's think of a student walking to class. A student walking to class, here's the school. So they might start off here and they got to go down a hallway and be able to go over here to their class or something. And they're going to have to slow down for other students in their way, or maybe they're going to have to walk a little bit quicker because they don't want to be late or something like that. So a student walking to class, rarely are they ever going uniform motion. A car, rarely are they ever going uniform motion. Now, a rocket launching into space, let's think about a rocket. A rocket's going to start off, here's the Earth. I know the Earth isn't red, whatever, but a rocket's going to start off here. And it's starting off technically going 0 kilometers an hour, 0 meters per second, right? The rocket starts on the launch pad, and then it launches into space, and then eventually it orbits the Earth, right? So it starts off going 0 speed and then ends up going something. So it's not traveling at a consistent speed, and it's definitely not traveling in a straight line. So no. So rarely do things ever travel in uniform motion. And uniform motion is kind of this idealistic version of motion where it's very easy to predict what's going on. It's very easy to analyze its motion. But unfortunately, that's just not the case. That's not that's not a very realistic scenario for a lot of different things. So instead of talking about things with uniform motion, we usually talk about things with non-uniform motion, and we like to talk about their average speed. So very few objects undergo uniform motion. Most objects will either speed up or slow down. Maybe they'll go in a different direction, something like that. For all our objects, regardless of uniform and non-uniform motion, we can describe their average speed. And their average speed is defined as the total distance. Oh man, that's not how you spell total. Goodness gracious. The total distance, and that term distance means something very specific. Remember, and we'll kind of talk about it again. The total distance that an object has traveled divided by the total time over which the distance occurred. And we use a very specific formula that's in your formula book. So this is page 5 in our data booklet. And you can see when we're trying to calculate the average speed, remember the right-hand side, this box here is actually really super important for you to kind of just know that it exists, I guess. If you're trying to calculate the average speed, well, average speed is V. And it's typically measured in meters per second, but it doesn't have to be. So we take a look, okay, we want to calculate V when I look at all the equations, and we're going to use most of these equations by the end of the semester. V is equal to delta D over delta T. So let's try that. V is equal to delta D over delta T. And all that means is that V, remember, is the average speed. I should say average speed. And it's equal to the total distance. Or I guess I should say change in distance. Delta means change in. So change in distance, and then divided by the change in time. So it's a relatively easy calculation to do. V equals D over T is usually how we say it. Okay, all right, perfect, no problem. I'm just going to write that as kind of the first version of this formula. So average speed is equal to the change in distance divided by the change in time. No problem. But let's take a look at this and let's think to ourselves, well, this equation's fantastic if we're trying to solve for V, if we're trying to solve for the average speed, but it's not amazing. This is not super helpful if we're trying to find or isolate one of the other variables, okay? So there are some other versions of this equation. There are different ways of writing it. V equals delta D over delta T. And so let's rearrange for delta D. Let's say we had equation or a question, and it said that it wanted us to find the change in distance, but it gave us both of these. Well, all we have to do is rearrange this. All we have to do is rearrange this to be able to, so I don't know why my software is glitching out here. All we have to do is be able to rearrange this for delta D. So let's do that right now. So let's rearrange for delta D. If I want delta D by itself, all we have to do is do the opposite operation of what's currently happening. I see delta D divided by delta T. What's the opposite of dividing something? Yeah, absolutely. It's multiplying by delta T and multiplying by delta T. And so our new version of our equation is, so we've got V times delta T on the one side equals delta D on the other. So if we, remember, we can always just swap the entire right-hand side and the entire left-hand side. We'll just reverse the equation. That's fine. So delta D equals V times delta T. Perfect. That's the other version of the equation. Okay, so that's that one. So if we want to get average speed by itself, we'll use the first version. If we want to get average or the change in distance, we'll use the second version. And there's a third version, and hopefully it's not too much of a stretch. That's the version that has the only other variable that we want to look for, delta t. So now I want to bring you back to the very first equation that we started with, v equals d over t. If you're looking for time, time can never, ever be in the denominator of a fraction if you're trying to isolate for it. So it can't be in the bottom. So if you ever see a variable that you want to solve for it, you want to get it by itself or isolate it, you got to get it out of the denominator. How do you do that? Well, you usually multiply everything by it. So that's exactly what we did here. We multiplied by delta t, and we ended up with this. Delta d equals v times delta t. Well, if we want delta t all by itself, we got to do the opposite of what's happening here. We got to divide by v. And when we do that, the v and the v cancel, and we're left with delta t is on the right-hand side, but it's all by itself now. Hopefully you realize the v's have canceled each other out, and we're left with delta t. Delta t is equal to delta d divided by v. Now, I just want to point out something to you, and that's what happened when we tried to get delta t by itself. Well, in the end, it basically swapped places with v. This thing and this thing ended up swapping places. So just be aware that that's kind of a shortcut to be able to get delta t all by itself. Okay, now what we want to do is we want to figure out what was the average speed of each car in the video. So let's go back and let's kind of check that out. Okay, so in the video, the blue car started here, right? The blue car started here, and it went this way, and it went 1.30 kilometers, and it took a total of 10.0 seconds. And the red car went all the way around this way, that way. So that was the distance that it went. Remember, we went over this video on Friday. The distance that it went was 1.24 kilometers, plus it went up here 1.3. So this distance is the same as this distance. So 1.30 kilometers. And then it backtracked on 63rd Ave the same distance that it originally went, 1.24 kilometers. Perfect. So when I add all that up, 8, 2, 3 is 7, 3.78 kilometers. And it took a total time 12.0 seconds for that to happen. So when we go in here and we see, okay, what was the average speed of each car in the video? Let's do the red car over here, and we'll do the blue car over here. The blue car was easier to deal with. It went 1.3 kilometers, okay? So the average speed is the total distance divided by the total time. So it went 1.30 kilometers in 10 seconds, sorry. So it went 10 seconds. So this is not in IUPAC units, okay, but that's totally fine. So 1.3 divided by 10 on my calculator is going to be 0.13 kilometers per second. I'm just using the units here. We got kilometers per second. Now, typically we want these in meters per second, so we could turn this into, if I were to do this, kilometers, so this would be 1.3 times 10 to the 2 meters per second. Okay, so I want to keep my significant digits. So that was the blue car. Let's do the red car. The red car's speed was its total distance or change in distance divided by the change in time. So the change in distance that it had was 3.78 kilometers. And it took 12.0 seconds for that to happen. So when we're doing this calculation, 3.78 divided by 12 is going to be 0.315 kilometers per second. And I could turn the kilometers into meters. I just got to move the decimal 3 times to the right. So that's 315 meters per second, which is insanely fast, by the way. I just wanted to make the video quick, so I made them going really super fast. But we want to maintain our same number of significant digits. So remember, it's kind of hard to compare this number and that number unless they're in significant digits, so or in scientific notation. So I've got 3 digits there and 3 digits there. Oh, sorry, I should have done 3 digits here. Jeez Louise, sorry. So instead of 1.3 times 10 to the 2, it should have been, because this is 130, so this is 130 meters per second. Here, 315, that's good. We've got 3 digits, 3 significant digits, and 3 significant digits here. So I should have 3 significant digits. So that's fine. So when we compare the speed of them, the red car was moving at 315 meters per second. The blue car was moving at 130 meters per second. And so, yeah, absolutely. When you watch that video again, you can tell that the red car is moving way faster than the blue car. Now, I just want to do some examples for you, and they're not going to be as complicated, but this was just like a very visual example. Now, the way I want us to do our problems is I would like us personally to organize all the information kind of on the side. So typically in a physics problem, we'll read the question first, and then I want us to summarize the information over on the left-hand side. So I'm going to separate everything using a squiggly line. Perfect. A person walks 10 meters away from a stop sign in 5.00 seconds. What is the average speed of this person? Well, let's go through here and let's kind of underline or let's circle some really crucial information. A person walks 10 meters. So that sounds like a change in distance. 10 meters away from a stop sign in 5 seconds. Seconds, so this is dealing with time. 5.00 seconds. And then what is the average speed? It's asking a question about it, so it wants us to find average speed. So how are all of these things related? Well, they're related through the equation V equals delta D over delta T. Now, the thing I want to ask myself is, which one of these variables do we want to solve for? We want to solve for average speed. So this is what we want. So the formula is already isolated for the variable that we want. We don't have to do a bunch of extra work here. We can just what we call plug and chug. So plug the numbers into our calculator and let the calculator do the hard work for us. So I want speed, and we're given distance and time, so this is going to be hopefully pretty easy. Average speed is the distance that we traveled, 10.0 meters, divided by the time that it took, which was 5.00 seconds. So when I do that, 10 divided by 5 is 2 meters per second. That's what my calculator is going to give me. If I put 10 divided by 5, it's going to give me 2. But there's a pretty glaring problem with that. Up on the top, I've got 3 significant digits. And down on the bottom, I also have 3 significant digits. Now, because I'm multiplying or dividing, either of those two things, which I am doing, I'm dividing. So because I'm multiplying or dividing, I need to take the lowest number of significant digits. I've got 3 on the top here. That's how precise my measurement was. I've got 3 on the bottom. That's how precise my measurement was. So I need 3 in my answer. So the way I can represent 2 to 3 significant digits is 2.00. That represents that I have a precise speed up to, that digit, and up to that digit, right? But past that digit, I don't know. I don't know if the next value is going to be a 0. I mean, I'm only estimating that this second 0 is a 0. So that's my answer to the correct number of significant digits. Now, on a quiz or a test or something like that, you would get 1 mark for the formula. You would get 1 mark for substituting the numbers into the formula, and you have to include your units every time. And then I would get another mark for the correct answer to the correct number of significant digits with my units. Now, when we're doing this, I mean meters divided by seconds will give me meters per second. So what does that mean? What does average speed mean? Well, that means on average, I was traveling 2 meters in every 1 second. So in the first second, I went 2 meters. In the next second, I went another 2 meters. In the next second, I went another 2 meters. Blah, 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 blah. That's what it means. Okay, I'll stop rambling and I'll keep moving on here. The Earth moves at an average speed of 107,000 kilometers an hour. What distance does the Earth travel in a 24-hour period? So if that's our speed is 107,000 kilometers an hour, squiggly line. What distance? It's asking us for the distance. So what distance does the Earth travel in a 24-hour period? So time is 24 hours. Okay, let's try this out. I'm looking for distance, and I know that they're related by this formula. Now, if I want distance all by itself, I got to do the opposite operation. So I have to multiply by delta t on both sides. Delta t and delta t cancel. So I should get delta d is v times delta t. Good. So you're going to get 1 mark for this, for showing me the rearranged formula. You don't get any marks for summarizing the information, but it's going to be super helpful later on. So distance is velocity times time. So we have 107,000 kilometers every 1 hour. I'm just trying to make sure that you understand that this is what speed is. Speed is that we're traveling on average 107,000 kilometers through space in every 1 hour. So if it says how far do we travel in a 24-hour period, so times 24 hours. When I do this, hours and hours cancel out, and I'm left with kilometers, which is good because we're looking for distance. So when I do this on my calculator, I get a massive number. I get a number 2,568,000 kilometers. That's how far the Earth travels in 24 hours, in 1 day. Now, let's take a look at this. I correctly gave the equation, the rearranged equation. Good, that's worth a mark. I correctly substituted in all the numbers with their units. Every time you write down a number, you got to write down what the unit is, right? 107,000, if you just write down 107,000, that doesn't mean anything to me. I don't know, 107,000 bananas? I don't know, 107,000 seconds? I don't know. What are you talking about? Okay, so I wrote down a number with a unit and a number with a unit, and I multiplied them. I got a number with a unit, But the very last thing I got to think about is significant digits. I see 6 significant digits here and only 2 significant digits here. So I need to round to 2 significant digits. So my real number, my real answer is 2. The 5 is going to get rounded up to a 6 times 10 to the power of, well, this is where the decimal is, 1, 2, 3, 4, 5, 6 times 10 to the power 6 kilometers. That's how far the Earth travels in a 24-hour period. Perfect. So now I have my answer with units and correct significant digits. Perfect. That's what we're looking for. A couple more examples. If you're running around the track during gym class at a speed of 3.24 meters per second, how long would it take you to go around the track twice? And twice is 400 meters because it's usually, 800 meters because it's usually a 400-meter track. So what are we going to do? Squiggly line. We're going to go through and summarize our information. A speed of 3.24 meters per second. Speed of 3.24 meters per second. How long will it take to go around the track? How long will it take? What does that sound like? How long will it take? Sounds like they're asking us for the time. And then they give us a distance, right? 800.0 meters. Perfect. So V equals delta D over delta T. Now, if I want delta T, all I have to do, this is the shortcut that we were talking about earlier, all I have to do is swap V and delta T. So because what I'm going to do is I'm going to multiply by delta T on both sides, and then I'm going to divide by V on both sides. So V, delta T. So the V and the T, they swap places, essentially. So here's our new formula. Delta T is delta D over V. So I get a mark just for writing that out. I get another mark for substituting in the information. 800.0 meters divided by 3.24 meters per second. So when I do that on my calculator, I get an answer of 246.91358, blah, 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 blah. And my units are, well, meters and meters canceling, and the seconds moves up to the top. But, I mean, let's just think about it. If you have a distance divided by speed and you're saying you're going to get a time, well, time is going to be measured in seconds, right? So let's answer this to the correct number of significant digits. Let's look back here. Up on the top, how many significant digits is this? 8000. That's 4 significant digits. How many on the bottom? I see 3. So I have to round to 3 significant digits. And because it includes the decimal, I don't have to use scientific notation. So 246 is actually going to round up, because the next digit's a 9, to 247 seconds. That is the answer. One more example, and we're going to move on. I'm going to get you to do some questions for me. A student is walking to her social class, from her social class to her science class. Unfortunately, she needs to go to her locker first. She walks 40 meters north in 20 seconds. So let's say she's here. So she walks 40 meters north in 20 seconds. And then she stops at her locker for 15 seconds. Then she heads 85 meters south. In 62 seconds, what was her average speed? Okay, well, let's think about this for a second. She walked, it's asking for an average speed. Speed is distance over time. Do you know the change in distance, the total distance? Now, I need you to remember back to what we were talking about on Friday. Distance is all of the individual distances. How much ground has this person covered? And so she went 40 meters. I get it's in the north direction, but that doesn't matter. For distance, distance is a scalar. We don't care about a direction. So she went 40 meters, and then she went 85 meters. So that's a total of 125 meters. So she went 125 meters. And then the total amount of time, she took 20 seconds plus 15 seconds plus 62 seconds. So 20 plus 15 is 35 plus 62 is 97. So she took 97 seconds to do that. So she ended up going a total of 1.28865 blah, 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 blah meters per second. But I got to round this to 2 significant digits. So it's going to be 1.3 meters per second. She was traveling an average speed of 1.3 meters per second. So what I want you to do is, now that we're done the video, now that we're done, these notes, what I want you to do is I want you to move on to the next page, and I want you to try these 5 questions. That's all it is, 5 questions, okay? Try them out. The answers are going to be in the notes for today, the filled out notes. Let me know if you have any questions. Again, I'm available from 10:45 to 11:15 every single day. Nobody really has answered a question that much in the last little while. So if you log on, you're probably going to be the only person there with me. So don't be afraid to ask me any questions. Thank you very much. Peace.